Okay, let's see. We've got the graph of f prime here, and f is continuous, means no jumps, gaps, holes, anything like that's connected. F of 3 is 0, so I'm going to sketch f. I know that f of 3, nice scale there, is 0. So I'm graphing f. Right? Okay. So it tells us from, now I'm going to write this time, I have to change it since I got to get it to go through this point. But this tells me, this part here tells me that the slope, f prime, is 1 between 0 and 2. So between 0 and 2, let's just say it goes like this, the slope would be 1. And then from 2 to 3, right, the slope is negative 1. So from 2 to 3, the slope is negative 1. So that means it's going to go down, down 1 over 1, right? So that's going to miss this point right here that I'm trying to hit. So I'm going to do it like this. I'm going to go up 1 over 1. And then the slope is 1 this way. Down 1 over 1, down 1 over 1. Does that make sense? So the slope on this part right here is 1. That's what this says. This is negative 1, which is this guy. And then from 3 to 4, the slope is 2. So I'm going to go up 2 over 1. And then the slope from 4 to 6 is negative 2. Here's 6, negative 2. So down 2 over 1, down 2 over 1. See how we're counting this? And then from 6 to 7, the slope's 1. So if I keep carrying this out to 7, it's going to go up 1 over 1. Okay, does that make sense? So we're just matching these slopes with the slope of the original function f. Okay? If this was curved, I wouldn't be able to be this precise about it. We'd just be estimating like we've done in the past. Okay, 55. Use final thermal calculus to find the area under the curve. So here's x squared from 1 to 4. So we want to know what this area is. Well, the integral from 1 to 4 of x squared dx. See, we've used this already today quite a bit. X cubed over 3 from 1 to 4, which is 4 cubed over 3 minus 1 cubed over 3. Whatever that might be, 4 times 4 is 16 times, so 64 over 3 minus 1/3, which is 63 over 3, which is 21. Square units. Alright, 73. Calculate the derivatives. Okay, so 73 is going to be, this is 73, sine of x cubed squared, because I substitute this into here for t. And then the chain rule is the derivative of the inside. That x cubed is what's on the inside. So times 3x squared. So it becomes 3x squared, because we want to write this in front of the sign so there's no confusion. Sine of x to the 6th. Okay, 74. I need to rewrite this as negative derivative of 3 to cosine of x, because I switched the limits, so it makes the integral negative e to the t squared dt, so that becomes negative e to the cosine squared of x times the chain rule, the derivative of the cosine, times negative sine of x. So it becomes, positive, let's write that as e to the cosine squared of x times sine of x. Okay, 75. I'm going to write this as the derivative of, see, I've got to have that going, if I'm going to take the derivative from a constant to my variable, but notice 0 is between negative x and x, so I can rewrite this as negative x to 0, e to the negative t to the 4th dt, plus the integral from 0 to x e to the negative t to the fourth dt. And then I've got to get the constant on the bottom, so this is the derivative of negative 0 to negative x e to the negative t to the fourth dt plus the integral from 0 to x e to the negative t to the fourth dt. So now I can just take the derivative of each one. So the derivative of the first one, this negative sign stays there. E to the negative x to the fourth. And the chain rule is a derivative of that, negative 1. Plus, and then the derivative of this side is just e to the negative x to the fourth. Simplifying, we get e to the negative x to the fourth, because negative x to the fourth is x to the fourth, plus e to the negative x to the fourth, which is 2e to the negative x to the fourth. Okay, I think we're good on that one. And 79, last one. Well, this is, again, I was doing this on a separate video.